During our visit to the PVT lab, we gained a hands-on perspective on the fundamentals of pressure, volume, temperature analysis. This type of analysis is used to study how reservoir fluids behave under varying pressure and temperature conditions. It plays a vital role in reservoir characterization, production planning, and the design of equipment, both at the surface and downhole. The visit helped us understand how essential PVT data is for effective reservoir management. By analyzing how fluids behave in the reservoir, engineers can design better production strategies to maximize hydrocarbon recovery. It also supports key decisions like well placement, flow control, and the design of surface facilities. One of the most important concepts we explored was phase behavior. In the lab, we observed phase diagrams that illustrate how fluids transition between liquid, gas, or two-phase states under different conditions. We learned about the critical point also, where the liquid and gas phase become indistinguishable, and phase envelopes, which define the boundaries within which specific phase exists. These diagrams are crucial for predicting how reservoir fluids will behave during production. We also studied key PVT parameters, for instance, bubble point pressure. It is the pressure at which gas begins to come out of solution in oil, and it is important for determining when gas will evolve. So the second one is the solution gas-oil ratio, shows how much gas is dissolved in oil at reservoir conditions. Oil formation volume factor, it will compress the volume of oil in the reservoir to its volume at the surface. And lastly, we also discussed about the viscosity, which significantly affects flow rates. Fluids with lower viscosity flow more easily and usually lead to higher recovery.
So, another concept we covered was the gas compressibility factor, which is Z factor. This Z factor indicates how much real gas deviates from ideal gas behavior, critical in high-pressure gas reservoirs. We also touch on interfacial tension and wettability, which influence how fluids move through the porous reservoir rock and are especially important in enhanced oil recovery techniques. Next is PVT lab equipment. Seeing the lab equipment in action helped us to connect theory to practice. The PVT cell allowed us to simulate reservoir conditions and observe phase behavior in real time. We watched how pressure and temperature adjustments cause changes in fluid states. We also saw a viscometer used to measure fluid resistance to flow, and a gas chromatograph that breaks down fluid samples to analyze their chemical composition. Overall, the visit to the PVT lab deepened our understanding of how these complex properties are measured and how they influence real-world decisions in reservoir engineering and production operation. It was a valuable experience that brought classroom concepts to life through practical, hands-on exposure.
Next is the PVT analysis report. The objective of this analysis is to identify the saturation pressure of the reservoir fluid, to calculate the compressibility above and below the bubble point, to determine the optimum separator conditions, and to analyze and compare the formation volume factor (VO) and solution gas-oil ratio (RS) using experimental data, Basquez and Beck's correlation, and the Excel plugin. The first one is saturation pressure. Saturation pressure or bubble point is the pressure at which gas begins to come out of solution. From the experimental data, we observed that RS remains constant at 694 SCF/SCB, and BO peaks at 1.399 until the pressure drops below 3086 psia. After this, RS declines and BO decreases, the classic indicators that gas is separating from the oil. Therefore, we identify 3086 psia as the saturation pressure. This value aligns with results from both the correlation and plugin, confirming its accuracy. For compressibility analysis, oil compressibility (CO) indicates how sensitive the oil volume is to pressure changes. In the report, CO is provided for pressure above the bubble point. For instance, at 7000 psia, CO is 1.1 at exponent -0.5 SIP and increases gradually as pressure approaches the bubble point. This trend, increasing compressibility as pressure decreases, is typical and expected. Below the bubble point, CO was estimated based on the slope of the BO versus pressure curve. Here, BO decreases more sharply, indicating that compressibility is higher below the bubble point. Correlation and plug-in estimates support this trend and match the report data closely. For optimum separator conditions, it maximized oil recovery while maintaining stable fluid properties. According to the test results, the best performance was achieved at 65 psia and 97 degree Fahrenheit, with a GOR of 674 SCF over STV and a BO of 1.399 RB over STV. This pressure gave the highest liquid yield while maintaining reservoir gas content. The API gravity remained stable, and this setting gave the best balance between gas removal and oil shrinkage. Hence, we identify 65 psia as the optimum separator pressure.
For BO versus pressure comparison plot, this plot compares the formation volume factor BO against pressure using experimental data, Vasquez and Bax correlation, and plug-in results. The trend is as expected. Above bubble point, BO increases with pressure and levels off. At bubble point, BO reaches a maximum value of 1.399. Below the bubble point, BO declines non-linearly, reflecting increased compressibility. The plug-in shows a slightly higher BO than experimental values, but follows the same shape, and the correlation closest matches both trends. RS pressure comparison plot. This plot shows RS, the solution gas-oil ratio, versus pressure. Again, we compare experimental data, Vasquez and Bax correlation, plug-in estimates. We see a flat trend above the bubble point, where RS holds constant at 694. Once pressure drops below bubble point, RS decreases rapidly, showing gas liberation from the oil. At pressures above the bubble point, RS remains constant and equal to its value at bubble point, obtained from the separator test. No gas is released at this stage. So, for pressures above bubble point, RS is equals to RS obtained at separator test. RS at pressures below bubble point, gas starts evolving from oil. RS is calculated using DL and separator test data. RS decreases with pressure as more gas comes out of the solution. RS is obtained by this equation. We'll be explaining on how oil formation volume factor and solution gas-oil ratio are determined from the combination of PVT test data, specifically using CCE, DL, and separator test. We'll explore how these combinations are used above and below bubble point pressure. CCE, fluid is expanded in a closed system, keeping its composition constant, simulates pressure decline above the bubble point. Separator test, a two-stage test, first stage separator at intermediate pressure, followed by flash to surface, provides surface volumes and helps calibrate RS and BO. Differential liberation simulates pressure depletion below the bubble point. At each step, evolved gas is removed, mimicking natural production. By combination of these tests, we generate realistic estimates for BO and RS throughout the reservoir pressure range. BO at pressures above bubble point. The oil is undersaturated. BO is calculated using combination of CCE and separator test data. As pressure drops, BO increases slightly due to oil expansion. At bubble point, BO reaches its maximum value, which is obtained from the separator test. BO at pressures below bubble point. Oil becomes saturated. Gas comes out of solution. BO is estimated using the combination of DL and separated test data. As pressure declines, BO decreases because gas evolves from oil and reduces its volume.
So, summary of what me and my friend have learned from this project. So, this project has helped me and my friend to connect hands-on lab experience with technical analysis of reservoir fluids. During the PVT lab visit, I have learned about key concepts like bubble point pressure, formation volume factor, and solution gas oil ratio, all of which directly informed in our report. Seeing how phase behavior is measured in real time has helped me to identify the bubble point at 3086 psi and interpret the formation volume factor and solution gas oil ratio trends above and below this point. The labs focus on compressibility and phase envelopes also help me analyze pressure-volume relationships more accurately. So the equipment that I have saw, like the PVT cell and viscometer, has gave context to the experimental data we used and supported our determination of optimum separator conditions at 65 psi. So overall, to conclude, the lab visit has deepened my understanding of fluid behavior and its impact on reservoir performance, which directly enhancing the quality of our analysis. That's all from us. Thank you.